Hello, chemist. I know. How in the world can she sound worse instead of better? But yeah, yeah, there's life. I guess I'm very grateful that I can record these for you. All right, let's talk about buffers some more. All right, so we looked at what happened when you added an acid or a base to a buffered system. Well, now let's ask the question, how do I choose a buffered system? What kind of a buffer do I need if I want, say, to use a system that is using a pH of 7 or a pH of 4? And so we're going to play with that Henderson-Hasselbalch, and we're going to have it tell us, well, where would you like this buffer to happen? I'm going to go over to the whiteboard. Clear that. All right, choosing a buffer. All right, now the first thing is you want to choose a buffer that's very close to the pH that you want. So choose a buffer. Well, that's a B. A buffer with a pKa close to the desired one, to the desired pH. And then if the pH is higher, okay, so if it's more basic, you need to add more of the base portion. If it's lower, you're going to add more of the acid portion. But you need to be very close. All right, so let me show you. So for instance, let's do vinegar. So HAC for a buffered system, the Henderson-Hasselbalch says the pH is equal to the pKa plus the log of the acetate over the acetic acid. Okay, so ideally, the pH will equal, okay, so the negative log of 1.8 times 10 to the minus fifth is 4.74 plus the log of the acetate over the acetic acid. If these are equal, okay, if these two are equal, and I'm just making these numbers up, we're going to say it's 0.050. And now keep in mind, this can be molarity, or with buffers, we can convert to moles. But if I had that, the pH is equal to 4.74 plus the log of 0.050 divided by 0.050. That is the number 1, and the log of number 1 is 0. And so if that is the case, the pH is the same as the pKa if they have the same amount of moles, okay? All right, so what would be the use for this buffer if I needed one close to 4.74? All right, let's say that I need one at 5. All right, so we're still going to use acetic acid, but if I need it at 5, right here, pH is equal to 4.74 plus the log of the acetate piece over the acetic acid. Well, how am I going to change this buffer so that it will work? So you set them up like this. So if you want a pH of 5, But right now, you have a pKa of 4.74, and it will tell you the ratio that you need to put in. All right, so negative 4.74 from both sides. And where's my calculator? So 0.26. So my ratio needs to be 0.26. So the log of the acetate over the acetic acid needs to be 0.26. And if you want to get out of the log, take the anti-log. (1.82). All right. Now, first of all, this number is greater than 1. Did we expect the base, the acetate piece, to be bigger than the bottom piece? And the answer is yes, because the pH is greater than the pKa. So we have to have more of the base piece. All right. How much more do we need? Now, this is just a ratio, and that ratio means 1.82 times of the base to 1 of the acetic acid. Now, notice it's not giving you exact quantities, it's just a relationship or just a ratio. So we have to choose one of them to start. Okay. So if you have 10 mils of the vinegar, this ratio will help you figure out how much acetate. Okay. So I'm making that up number now. This is my ratio. And so I'm going to take 10 mils of 0.1 molar acetic acid, and I'm going to use the ratio to tell me how much vinegar that I need, or sorry, how much acetate that I need. Now the power, remember, is in moles, not the milliliters or the molarity. So the first question is, well, how many moles of my vinegar do I have in that 10 mils of 0.1? So 10 mils converted out. So 0.10 moles. And I think that should be 2 zeros, but let's do it. 10 divided 1,000 times 0.1. Yep, 0.001. So in this 10 mils, I have 0.0010 moles of my vinegar. Okay. Well, that's great. But what I'm asking is I need to make a buffer. So I need to add some of its conjugate base in there. And I need to know how much to add. And so that's where I'm going to use my ratio. I know that the acetate divided by that 0.0010 moles has to be the ratio of 1.82. And so my acetate number of moles has to be 0.00182. So what I need to add together is this many moles of the vinegar and this many moles of the acetate, and then I will have a buffer that has a pH of 5. Well, great. That's how many moles of the acetate that I need, but how many milliliters? Okay, well, that depends on which bottle you grab. Okay, I know I have to have 0.00182 moles of the acetate. So I don't care whether you go grab a solid off the shelf or if there is a solution on the shelf. I now know the moles. We just have to ask, well, what's available? And so let's say there's also available a zero point 0.1 molar sodium acetate solution. Oh, well, guess what? 0.10 moles. Remember, it's just a tool that will get you out of moles and into volume. And so let's see, divided by 0.1, and let's get out to milliliters. Whoa, 18.2. Gee, that should have been obvious. See, if you like ratios, this will be very obvious math. All right. So if I add 18.2 milliliters of a 0.10 molar solution of sodium acetate to my 10 milliliters of my zero point 0.1 molar acetic acid, I will have 28.2 milliliters of a, not zero point 0.1 molar anymore, remember, but I will have 28.2 milliliters of a buffer of pH 5, a buffer of pH 5. So we now have 28.2 milliliters of a buffer with a pH of 5. And inside that 28.2 milliliters, I have 0.0010 moles of acetic acid, and I have 0.00182 moles of my acetate. All right, that either made perfect sense or it was like, I'm not sure where you're going. So we're going to do the exact same thing. I'm just going to choose a different number. All right, so instead of a 5, let's take it a little more acidic. So let's say we need a buffer with a pH of, well, let's say 4.6. Okay, so we're still going to use the vinegar, And so I need to ask, well, what ratio of my acetate to my acetic acid do I need? So if you want a buffer of a pH 4.60, vinegar pKa is 4.74 plus the log of the base piece over the acid. So I'm asking, hey, what ratio do I need? So I'm going to subtract 4.74 from both sides. And let me see, so this is a negative 0.14, and I know, but I'm not trusting that in my head, so I'm going to use the calculator too. Bye. All right, is equal to the log of the acetate over the acetic acid, but I don't want to be in the log, so I'm going to take the anti-log. Now notice this time there's a negative. Okay, that comes from the calculation. I don't just add that. The reason it's negative this time is because I subtracted 4.74 from both sides. All right, so my acetate over my acetic acid ratio is 0.72. How many sig figs do I get? Let me see. 2 after, so 2 totals. 0.72. All right. Notice that's less than 0 or less than 1, but I expected that because it was more acidic than the pKa, which means I need more or excess acid to get this particular buffer, okay? Which means the bottom piece, the vinegar, needs to be more than the acetate. So mathematically, that ratio should be less than 1. All right. Now, technically, the answer is done. Hey, what ratio do you need? It is 0.172. So a way that you can see this is for every one acetate, you would need 1.72 vinegar. Okay, it's just a ratio. So however you want to set that up. But here you have to know how much you have of one of them. And again, I'm telling you, you get 10 milliliters of the zero point 0.1 molar vinegar. So we're going to get out of the milliliters. Okay, so I'm setting this. I went to the shelf and I grabbed 10 milliliters of my zero point 0.1 molar vinegar. Now that I have one of them fixed, it will tell me how much of the other one I need, though. So I have, if I want to know the acetate, I have 0.010, whoops, two zeros, 10 moles. But this time my ratio is 0.72. So my acetate is going to be 7.2 times 10 to the minus fourth. Do that math again. Yep. Oh, okay. What does that mean? Okay, that's just telling me how many moles of my acetate I need. Now I need to look on the shelf. Do I want to go grab a bottle of this solid? Do I want to grab, some kind of a solution? So just like the last problem, I'm telling you what is available is that zero point 0.1 molar solution. So how much of it do I need? Well, I know that for every 0.10 moles, that is 1 liter. And let's just go all the way to milliliters. I need 7.2. Okay, now I haven't made my buffer yet. What it has told me is I need to take 7.2 mils of my zero point 0.1 molar sodium acetate, and I need to add that to my 10 mils of 0.10 molar, it's supposed to be a capital M, acetic acid, and I will have in the end 17.2 milliliters of a buffer of pH 4.60. Beware, beware, beware. Okay, I do not have 0.10 molar solution anymore. I've added them together, so if I want to know what their molarity is, I'm going to need to do the dilution, M1V1. But I do know that the total volume, 17.2, is a buffer that now has the capacity of 4.60. Okay, now let's go look at how we would choose that buffered situation. All right, I'm going to the notes here one more time, and I want to see if I list it here. I don't, so I'm going to go over the reference pages. All right, so here is how I came up with the ratio. Okay, I'm going to go to the reference sheets, and I have a little portion right here underneath those common pHs. This is not the complete list. Okay, I just put this list together so it was very visual. What you're really going to be looking for is the KAs. So you would go to the KA, you would go to the acid ionization list. But here's just some common buffers. So if you have lactic acid and lactate, its Ka is 1.3 times 10 to the minus fourth. So it has a starting place of 3.89. So if you had the exact same number of moles of lactic acid and lactate, you would choose 3.89, okay? And then you would play with, does it need to be more acidic or basic? All right, acetic acid, its starting point is 4.74. The carbonic acid hydrogen carbonate, okay, there's only one proton that's come off, has a pH of 6.37. Okay, now notice I said pH if you have the same number of moles. All right, and so I just give you a few here in a range. There are a lot more on your reference sheet, but of these ones, let's say I need, I need a buffer with a pH of 7.2. I would go to this list and I would find the closest one. And oh, right there. Because the closer you are, the better buffering capacity it has, because you have pretty much the same moles of the acetate and the acetic acid, or the base versus the um, um, acid portion. So the closer you can get, the better. And this one's really close. It's only off by 0.01. And so that's where I would start. So in this case, that's the buffer I would use. Sorry, had to cough. All right, so new question. Let's say I need a buffer of 5.6. I need a buffer with a pH of 5.6. So I go to my list, and who is the closest? Okay, so it's going to be one of these two, and can't do that math off the top of my head. So 5.6 minus 4.74, this one, how close is it? This one is 0.86 off, which still isn't bad. And how about 6.37? So 5.6 minus 6.37. This one is 0.77 away. So this one is actually closer. So that's the buffer I would use. And then I can plug it in, and it will tell me my ratio. And so we're going to go over to the whiteboard and do this one. So 5.6, and its pKa is 6.37. So 5.6, and this one happens to have a pKa of 6.37. All right, so 5.6 is equal to 6.37 plus the log, and I'm going to be really generic. I'm just going to say the base piece over the acid piece. And if I subtract that from both sides, negative 0.77 is equal to the log, the base over the acid. I'm going to take the anti-log, and so the base, that's a B, over the acid. The ratio in this case is 0. And I get two sig figs, 0.17. All right, that is less than 1. Okay, that's less than 1, which means the denominator is bigger, which means there's more acid in there than there is base. Is that what I expected? So I'm going up and I'm looking at my ratio. My pH is more acidic, okay, lower pH than my pKa, which means I need excess acid. That means the bottom, I need more A than I need B, and this ratio is telling me that. Okay, how much more? Well, now I have a number. And we would say, okay, which bottle do you want to grab off the shelf? But the important piece is we know the ratio. We know the ratio. All right. So when you are choosing yours on the handout, you are not limited. Okay. You are not limited to this list. You get to use anything in your KA list. And I know this is written sideways. Okay. But I'm going to limit you to only the mono products. So don't choose anybody that has multiples, at least at first. Okay. Don't choose anybody that has multiples. Stick with anybody that only has one proton. And then you would choose whoever is the closest to the pH that you need. But don't forget, you can use this entire list. You don't have to just use that tiny list that I have from above. All right, we go back here. Whoops, I don't know if I'm sharing it. There, now I am. Okay, so how are you going to choose a buffer system? You are going to figure out what pH you need, find the one with the pKa that is the closest, and then determine what ratio of the acid component and the base component needs to be mixed together. And then the next little video, we'll talk about, okay, now you've chosen what is its capacity, okay? How good is it? All right, so until next time, Jolly out.